This is problem set 37, where we're going to introduce the idea of entropy. So previously we talked about enthalpy, delta H, and enthalpy discusses the heat involved with the process, and so it tells us if something is endothermic or exothermic. Whoa, exothermic. In general, we like to say that things tend to go to a lower level energy state if possible. Things like to get to as relaxed a state as possible. Okay, and according to enthalpy, things that are exothermic release heat and therefore get to a lower level or a lower energy state. So according to that idea, we would say that water would like to get to its lowest energy state possible, which would be ice, solid water, because every time it goes from vapor to water or vapor to liquid, it releases heat, reducing its energy level, and then when it goes from liquid to solid, it releases heat, reducing its energy level. So the idea that things like to release as much energy as possible to get to the lowest energy state possible kind of leads us astray here when we're just using enthalpy to figure out if something's going to happen, right? Because that's the goal. The whole goal here is to figure out, using mathematics and thermodynamic principles, we want to figure out what processes are going to happen and what are not going to happen. Well, in order to do that, enthalpy is not enough. We need to introduce something called entropy. Okay, so entropy, the textbook definition, well, I guess I don't know the textbook definition off the top of my head, but entropy is generally thought of as the amount of energy dispersion in a system. How well is energy being spread out or dispersed in the system? A lot of people like to think of it as how much disorder is there. Things with more disorder have more entropy. Okay, and that leads us to the second law of thermodynamics. So as a review, the first law says that the change in energy of the universe is equal to zero. You can't create or destroy energy. The second law says that the change in entropy of the universe, the amount of disorder in the universe, is always increasing, or the change in entropy of the universe is always greater than zero for a spontaneous process. Okay. So that leads to the question, what is a spontaneous process? Spontaneous process is something that happens in real life. Okay, now there's some nuances to that. Certain things happen in some conditions and don't happen in other conditions. So a good example is like muffins rising in the oven. So I take muffin dough or muffin batter and I put it in the oven. The question is, in the oven, will the muffin dough rise? Well, it depends. Is the oven on or not? If the oven is on, in those conditions, those muffins rise, and therefore in those conditions, muffins rising is spontaneous. But muffins on the counter, under those conditions, muffins rising is not spontaneous because it doesn't happen. So spontaneous processes happen. And we'll talk a lot more about that this problem set as well as in the next problem set 38. Anyway, so the second law of thermodynamics says delta S of the universe is always greater than zero for things that happen, for spontaneous process. And just as a reminder, delta S of the universe equals delta S of the system, no subscript means system, plus delta S of the surroundings. So it is possible for the entropy of the system to go down. It's just that the entropy of the surroundings has to go up by more than the entropy of the system goes down for something to happen. So that's the second law of thermodynamics. And now let's talk about the third law of thermodynamics. It says that entropy equals zero for a perfect crystal at 0 Kelvin. Okay, so whereas with like enthalpy, we never really had a 0 point, and so everything that we dealt with was changes in enthalpy. All right, well, we have a 0 point for entropy, and as a result, if I said, what is the entropy of water, there is a value for that, okay, the entropy of water. Now, with enthalpies, we would say, what's the enthalpy of formation of water, which is the change in enthalpy of formation when you make water from pure elements. But with entropy, we have actual numbers for it because we have a 0 point, and that'll come up later. Okay. So let's talk a little bit about the second law a little bit more. Why is it that entropy of the universe always increases for things that happen? Well, entropy is really a statistical thing. So if I were to have a stack of papers perfectly stacked up, and I take them and I throw them up in the air, is it physically possible, or I guess we could ask the question, I throw them up in the air, what's usually going to happen? Well, those papers are going to spread out and fly around randomly, right? So that is the idea that entropy or disorder is always increasing. That's what's always going to happen. You throw those papers up in the air. But the question is, why does that always happen? Okay, and the reason is a matter of statistics and probability. So if I were to have these papers piled up, 1, 2, 3, 4, 5, 6, and I throw them up in the air, how many ways could they come and perfectly land 1, 2, 3, 4, 5, 6? Okay, there's only one way. And we call that one microstate. There's only one way that we can arrange that situation. Well, how many different ways could I throw them up in the air and have them be spread out randomly, okay, and just messy and dispersed? Okay, well, there's going to be like a ton. You know, virtually infinite for them to be random and messy. So if there's only one way for them to land up perfectly stacked, and there's nearly infinite ways for them to land messy and random, what's going to happen? Well, they're going to be messy and random. And so these statistics hold up and these probabilities hold up, especially when we're dealing with chemistry and molecules, because we're dealing with molecules in units of 10 to the 23rd molecules, right? So with a sample size that large, these statistics hold up, and as a result, theoretically and in practice, the entropy of the universe will always be increasing. Energy will always be dispersing more, just because statistically it's just tremendously, infinitely more likely to happen that way. Okay, so that is entropy, and let's talk about how we could change the entropy of a system. So there are a few ways. Well, there's lots of ways. A few to really think about. The first is phase. If I were to have a solid and turn it into a liquid, as soon as that happens, a liquid can move around more randomly, there's more ways to arrange it, and the energy can be dispersed in more ways. As a result, phase has a tremendous impact on the amount of entropy in a system. Secondly would be the number of particles. Okay, so if you think of, if I have one particle, how many ways could I arrange that? Only one. But if I had two particles, all of a sudden there's two ways to arrange them, right? So here's one particle, here's two particles with two ways. If I had three particles, all of a sudden there's 6 ways to arrange them. So you can see the more particles I have, the more ways I can arrange things, the more I can make things disorganized and disperse energy. So number of particles has a big effect. And lastly, the size of the particles. So for example, if I had a helium atom versus pentane, right, this pentane, it could flip around, right? It could go like that. It could go like that, right? There's a lot of different ways to flip it around and arrange that pentane, and so that pentane has more entropy. Similarly, if I had pentane versus this guy, okay, this has more entropy than this. Even though they're the same size, you can see that the straight molecule could be flipped around more here. This branch is being told exactly where it's stuck. Okay, there's less ways to mess that up. You can see the extreme case is if we had, again, same size, same molar mass, but now there's way fewer ways to flip around that molecule. Okay, so this would have the greatest entropy because of its size and its shape. So those are 3 big things to look at, and you'll see as we look at them today how to apply that. But there's a few other ways, other things to be aware of. If I have a greater volume, right, my things can move around further, and therefore I could have greater entropy. If I have a greater temperature, things are moving around faster, and therefore there's more disorder there and more dispersion of energy. So there's a lot of things that could affect it. These 3 are the 3 to really look at, and other ones to be aware of as well. Now, lastly, let's talk about how you can calculate entropy for a process, actually numerically instead of conceptually. And then we'll get into the problem set, and it should be pretty easy at that point. So if I'm trying to find the change in entropy of a process, okay, so the first thing I'll say is in certain conditions we have what we call a reversible process. which for you can think of as adding Q or adding heat with a no change in temperature. Okay, so really, when does that matter for us? 1, phase changes, we add heat without the temperature changing. And 2, when we're adding or removing heat from big surroundings is what I'll call it. I'm adding or removing heat from the world. So, for example, I light a campfire that burns, it releases heat into the world. Does the temperature of the world change? No, not really. So we call that that could be considered a reversible process, and as a result, what I'm about to talk about applies to it. So in these two situations is what you're going to see, but in general, in a reversible process, the change in entropy of something is going to equal the heat of that reversible process divided by the temperature. You could also write that as the delta H of that reversible process over the temperature that it happens at. Okay, so again, I'm adding heat, temperature's not changing. Okay, so we call it a reversible process. The two situations you see are phase change and the big surroundings, and you'll see that. And we can find delta S as Q over T, or delta H over T. Okay. The other idea, this really works for anything, but we really see it for like reactions, is when we use it a lot. The idea being that the change in anything is just the final state minus the initial state, right? That's how we define change. So change in entropy is final minus initial. Well, because I talked about up here, I said we know what zero entropy is. So we have entropy values for every molecule in certain conditions. And so really, for what this means for a reaction is just entropy final is just the sum of the entropy of the products. Entropy initial is just the sum of the entropy of the reactants. So if we have values for those entropies for each molecule, then we can just do products minus reactants. That'll give us the entropy of a reaction. Okay, so that's everything I believe you need to know for this problem set, so let's dive into it. What does it mean for a reaction to happen spontaneously? I'm just going to write that it happens. Now the textbook definition, which might be important to know, is a spontaneous process is something that once started continues on its own. Okay, so whatever conditions that, once it starts, it goes on by itself without having to add any more energy. Okay, but the practical definition is that it happens. Second law of thermodynamics, we said that's delta S of the universe is greater than 0 for spontaneous process. And because non-spontaneous processes don't happen, you'll sometimes see it just written as delta S of the universe is greater than 0, because there's no non-spontaneous process that would make it less than 0 because they don't happen. State the third law of thermodynamics in one sentence, and I said that over there, the entropy equals 0 for a pure crystal at 0 Kelvin. All right, define entropy. Again, we talked about this. Entropy is dispersion of energy, disorder. Yep. State 3 factors that might affect entropy. Wow, we talked about all this. So phase was one of them that we talked about. Then we talked about number of particles. We also talked about size. Right, and then we talked about volume, we talked about temperature, and there's other stuff too. 2 ways of calculating entropy change. So we said for a reversible process, you could use Q over T. We talked about for anything, you could use products minus reactants. Okay, some application. Which of the components in each of the following pairs has greater entropy? So remember, we're looking at 3 things: phase, number of particles, and then size of particles. So first off, 1 mole of S2 gas versus 1 mole of S8 gas. First look at phase. Well, they're both gas, so that doesn't help us. Number of particles, they're both 1 mole, so they each have 6.02 times 10 to the 23rd particles. Size of particles, S8 is bigger. Okay, so a bigger molecule can be flipped around and arranged in more ways. All right, 2, 1 mole of S8 gas, 1 mole of S8 solid. First look at phase. Solid, or a gas, has much more entropy, much more disorder than a solid. All right, 1 mole of O2 gas versus 1 mole of O3 gas. That follows the same logic as A. And the bigger molecule is better. Lastly, 1 gram of O2 gas versus 1 gram of O3 gas. Look at the phase. They're both gases. Number of particles. We have 1 gram of each. But O2 is lighter, and therefore you're going to have more O2s in 1 gram than you will have O3s in 1 gram. So there's actually more molecules of O2 gas in 1 gram than there are of O3 gas in 1 gram. All right. 4. Ice cubes melt in a glass of lemonade, cooling the lemonade to 10 degrees Celsius, from 10 degrees Celsius to 0 degrees Celsius. If the ice cubes are the system, what are the signs of delta S? System, surroundings, universe. All right, so ice cubes are a system, the lemonades are surroundings, and the whole glass is our universe in this problem. So, delta S is the system. What we're asking ourselves is, what's happening to the system? What's happening to the ice cubes? They're melting. That's a phase change. Okay, and they're getting more disordered when they go from solid to liquid, so that's positive. Now the surroundings, what's happening to the lemonade? It's cooling from 10 degrees to 0 degrees. It's getting colder, things are slowing down, so there's less dispersion of energy, so entropy must be going down. Okay, and then the universe. Okay, what is the real question when we ask about entropy of the universe? The real question is this spontaneous or not? Does this happen or not? When you put ice cubes in lemonade that's above the freezing point, do the ice cubes melt? Absolutely they do. So entropy must be positive because it's a spontaneous process. All right, adding sidewalk de-icer, calcium chloride, later in the problem they're going to call it salt, to water causes the salt to dissolve and the temperature of the water to increase. If solid CaCl2 is the system, what are the signs of delta S? System, surroundings, and universe? All right, so we're taking salt, we're dissolving it in water, the temperature of the water increases. So the system is the salt. Okay, it's going from being a solid to being aqueous, to being dissolved in water. Okay, so that is a greater entropy. It's more disordered, dissolved than it is as a solid. The surroundings, the temperature of the water increases. So that means that the surroundings entropy must be going up as well. Okay. And the universe, you have to ask yourself, does calcium chloride actually dissolve in water to melt the water? And they use that all the time. So yes, that does happen. And if you don't know that, that's okay, because if the system's positive and the surroundings positive, the universe must be positive. Okay. Number 5, we look at each of these. So remember, first is phase, then number of particles, then size of particles. All right, so we got liquid to gas. What are we saying? Which increases or decreases? Liquid to gas definitely increases. Solid to aqueous, that's phase, right? That increases, more disorder. Solid and gas down to solid, that decreases. Things are getting more ordered when they're solid. Gas to gas, gas and gas to gas, so that doesn't tell us phase. Number of particles, we have 1, 2, and here we have 2. That doesn't help. Size of particles. We've got NN and OO going to NO and NO. Okay, there's not really much distinction in the size there, and so that doesn't help us. So without numbers, I don't really know. I'm going to say that's pretty much close to 0 based on our methodology. Is it 0? I don't know. I'd have to look at numbers, but based on what they give me here, I can't tell. Solid to gas is increasing entropy for sure. Then we have solid and gas down to solid, so that's negative. Gas and gas down to solid, that's negative. Gas and gas to gas, that doesn't help. For phase, number of particles, we have 2, 3, down to 2. So because I have fewer particles, I must be making these things more organized. And as a result, it's going to be negative. Okay? All right, a particular reaction is spontaneous and has a delta S of reaction of negative 163 joules per Kelvin. What must be true about delta S of the surroundings? All right, so you know that delta S of the universe equals delta S of the system plus delta S of the surroundings. It tells us the reaction is spontaneous. That should ding, ding, ding in your head to tell you that delta S of the universe must be positive, which means delta S of the system plus delta S of the surroundings must be greater than 0, right, if the delta S of the universe is positive. And then it tells you delta S of the reaction is negative 163. So negative 163 plus delta S of the surroundings is greater than 0. rearrange that and see that delta S of the surroundings must be greater than greater than 163 joules per Kelvin. So I can do that mathematically with this inequality, but really, you can just think about it. I know that if it's spontaneous, the universe must be positive. If the reaction is negative 163, surroundings has to be positive 163 or bigger to make that a positive number. Okay. A particular reaction releases 25 kilojoules of heat into the surroundings, which are 27 degrees Celsius. If this reaction is spontaneous, how does this limit the possible values of delta S reaction? Okay, again, tells you the reaction is spontaneous, that must be positive. So let's write it down. We know that delta S of the system plus delta S of the surroundings must be delta S of the system and delta S of the surroundings must be greater than 0 because it says that it's spontaneous. Now it wants to know about delta S of the reaction, which is going to be the system. The reaction is always going to be the system, which means we need to know something about delta S of the surroundings. Well, it tells us 25 kilojoules of heat gets released into the surroundings. Remember, if we're dealing with big surroundings, that's like we consider that reversible, so we know how to calculate delta S. It's just Q over T, or delta H over T. So, I'm going to jump over here. Delta S of the surroundings is going to equal Q of the surroundings over T of the surroundings. Well, how much heat goes into the surroundings? It's 25. Well, it's released by the reaction, so it's negative in terms of the system, but we want Q of the surroundings. It's being released, so it's going into the surroundings. So it must be positive 25. The temperature of the surroundings is 300 Kelvin, or 27 degrees Celsius. That gives us 0.0833 kilojoules per Kelvin. There is our entropy of the surroundings. So I can do that here. So I know delta S plus 0.0833 is greater than 0. So delta S must be greater than negative 0.0833 kilojoules per Kelvin. There you go. All right, mercury is a liquid at room temperature and freezes at negative 38.9 degrees Celsius. What's the entropy change when 50 grams of mercury freeze and the enthalpy of fusion is 2.29 kilojoules per mole? Okay, and they give us the temperature. So we're just trying to find the entropy change of this. What's happening? It's freezing, right? Well, that's a phase change, right? And we said if we're doing a phase change, or at the temperature of the phase change, we can just do that the entropy is Q over T. So the heat freezing over the temperature. Well, what's the total heat of freezing? Well, it tells us the enthalpy of fusion, that's melting. So that means the delta H of freezing must be negative 2.29 kilojoules per mole. And I'm freezing 50 grams. Let's figure out how many moles that is. 1 mole of mercury, I believe it's 200.59 grams of mercury. That gives me 0.25 moles of mercury. Well, I know that when I freeze 1 mole, I get negative 2.29 kilojoules released. So I could do this. N delta H. My N is 0.25 moles. My delta H is negative 2.29 kilojoules per mole at a temperature of negative 38.9 plus 273, a temperature of 234.1. So all I did was find my heat, the heat involved with me freezing, my 50 grams, divided by the temperature at which I'm freezing, and I can plug that in. And I get that the delta S of that process is going to be negative 0.0024. And what's those units there? Kilojoules per Kelvin. Now, is this spontaneous or is it non-spontaneous? You might say it's negative there, which means it must be non-spontaneous, right? For the second law of thermodynamics says entropy must be increasing for something to be spontaneous. Okay, well, I'm pointing this out because it's an important distinction. The second law of thermodynamics says the entropy of the universe must be increasing for a spontaneous process. Here, we just calculated the entropy of the reaction, right? The reactions, or the freezing, right? That's negative because I'm going from liquid to solid. I'm getting more ordered, so my entropy is negative. Okay? But we know that stuff can still freeze, right? It's still possible for that to happen. And all that means is that for something to freeze, when the entropy of freezing is always going to be negative, that means the surroundings must be increasing in entropy by more than the system is decreasing by entropy when it freezes. Okay, so again, this does not tell me that it is not spontaneous, because this is the system. Delta S of the universe tells me if something is spontaneous or not. All right, the normal boiling point of ethanol is 78.3 degrees Celsius, and the enthalpy of vaporization is 38.56 kilojoules per mole. What's delta S of the system when 68.3 grams of ethanol condenses to its normal boiling point? Okay, well, we've got a phase change here. So we're condensing. That's going to equal the heat when it condenses over the temperature at which it condenses. What's a phase change? I'm going to have N condensing, delta H condensing over T condensing. Okay. I've got 68.3 grams. I need to get that to moles. Grams of ethanol. 1 mole of ethanol. I think it's 46. It is 46 grams. That gives me 1.485 moles of ethanol. Okay, so I got my moles of ethanol, 1.485. My delta H is 38 well, this is the enthalpy of vaporization. I'm not vaporizing, I'm condensing, so I need to use the negative value there. Over the temperature, 78.3 plus 273 gives me 351.3 Kelvin. And I can go ahead and plug that stuff in. Doing that gives me an entropy value of negative 0.163 kilojoules per Kelvin. There we go. And of course I could change that to joules per Kelvin. I could say it's negative 163 joules per Kelvin. There's nothing wrong with that. Okay, so that's how we calculate delta S for phase change, or if we're just wanting to find the delta S of the surroundings, those big surroundings, right? Okay. The following reaction plays a key role in the destruction of ozone in the atmosphere. Standard entropy change for this reaction, so the delta S of this entire reaction, is 19.9 joules per mole Kelvin. Use the standard molar entropies, just S naughts, in Appendix 4 to calculate S naught for CLO. So we're looking for this one. So we've got to look up the other ones. So let's see, Cl2, when you look it up, is 223 joules per mole K. O3 is 238.8 joules per mole K. Okay, and O2, remember, when we're talking about delta H as a formation, which we talked about in problem set 36, those are 0 for a pure element in its standard state. Okay, S values, though, are not 0 for a pure element. Okay, because, remember, we know what S value is. When S value is 0, it's for a perfect crystal at 0 Kelvin. This is not a perfect crystal at 0 Kelvin, so it's going to have an S value, so don't forget to look that up. O2 is going to be 205. Okay. And now they're trying, technically you can just look that up in the book, but they're trying to get us to find it. So we're going to find it. Well, we know for any process, the delta S of any reaction is going to be the sum of the delta S of the products, of the S of the products minus the sum of the S of the reactants. We're just doing, the change in entropy here is just final minus initial. That's all that's saying. All right, so we got 19.9 kilojoules per mole K equals products, which is going to be the S of our ClO plus the 205 joules per mole K minus our reactants, which is going to be 1/2 223 plus my O3. Okay, so now I'm solving for this one. So when I do that, and I get that the S naught for ClO is going to be 165.2 joules per mole K. Okay, so that's using products minus reactants. Now it says calculate the S naught value, the delta S value for the conversion of ozone to oxygen. So now we're looking for the delta S of this reaction. This reaction is really just, O3 to O2. But ozone to oxygen in the absence of chlorine atoms. All right, so here we're getting ozone into oxygen with chlorine. Here we're getting it without. Compared to the S naught value, the reaction with ClO. Okay, so we have the values for each of these. Right, we already looked them up. O3 is 238.8. And O2 is 205. Okay. So now I'm just going to do products minus reactants. So the delta S of this reaction is going to be products 3 times 205 joules per mole Kelvin minus my reactants, which is 2 times 238.8 joules per mole Kelvin. I do that, I get that the delta S for this reaction is going to be 137.4. There we have it. You can see the delta S for this process is 19.9. Delta S for this one is 137.4. Again, that doesn't tell us anything about the spontaneity, because these are both for the system. If we want to know about spontaneity, we'd need to have to know about the surroundings in order to figure out the universe. But there you go, products minus reactants. Okay, so we did two ways of, a lot of conceptual stuff, and then two ways of actually calculating delta S. One is for a reversible process, which means we're, in our case, either a phase change or we're talking about the surroundings. You can just do the delta S as the heat over the temperature. But in any case, if you have a reaction, you can find the S values for everything, and you just do final minus initial, in other words, products minus reactants. And there you go, that's entropy.